So, good day. Welcome to the another lecture. Shit. Okay. So, good day. Welcome to another lecture in plant modeling 2. Today we will be looking into the module 4, where where we'll be looking how we can couple processes. Till now we had talked about photosynthesis separately, stomatal conductance separately, stomatal water stress separately. We have looked into various equations that are used in these processes, and we also saw that it is not a linear set of equations. There are a number of equations, number of unknowns, how those various parameters used in the equations used for estimating photosynthesis, how it is obtained from temperature response curves, and there is a long list of equations that are used in obtaining these parameters and then predicting this process of photosynthesis, stomatal conductance. For stomatal conductance, we had looked into Bolberry equation, and now we also know that Bolberry equation considers that the stomata is not affected by any kind of water stress, and if we want to consider water stress, we have to use the stomatal water stress functions to include the water stress, stomatal conductance impacted by water stress. So all of these we know for all these processes are not occurring separately. All these processes are occurring interacting with each other. So BioCro has this facility to couple all these processes together and also predict whether it is photosynthesis or stomatal conductance. It is able to predict all these processes with the presence of the interaction of the stomatal conductance on photosynthesis and stomatal conductance. So before I go into most of it will be I can explain in the modeling, but before that how these interactions happen in the model is in the following way. So initially we give some initial values into the model, some initial guess value, which includes what is the incident ppft. So we know that light energy is estimated, or light energy is used in the form of photon flux density, photosynthetic photon flux density. So we give an initial value, incident value. This is not going to be an initial value, but it is going to be the actual value that we have. Then we give the actual value of leaf reflectance. We give an initial value of temperature of the leaf. Temperature of the air is again not an initial guess, but it is the actual temperature. Vc max, J max, TPU rate max, and RD. On these Vc max, J max, TPU rate, and RD, because these are the values that are obtained at a reference temperature of 25 degrees Celsius. Then B0, B1 is the intercept and the slope parameter or the Bolberry parameters for the Bolberry equation. We give the atmospheric carbon dioxide again, which is not going to change. So if you see oxygen, which is not going to change, stomatal water stress, again one estimated value that we have, we'll be using it as an input. Electrons per carboxylation doesn't change. Electrons per oxygenation is also a constant value. Beta psi 2 is a constant value. Boundary layer for boundary layer conductance is in moles per meter square per second is a stickers ഉണ്ടാക്കും stickers എന്ത് ചെയ്യാ ഗുരുവായൂരിനെ പോസ്റ്റ് ചെയ്തിരുന്നു. ബോറടിക്കാൻ തളരും. ഗുരുവായൂരിലാണെങ്കിൽ ഞാൻ ബോറടിച്ച് തളരും. അങ്ങനത്തെ ഉരുളും തുളരും. അവിടേക്ക് പോവും, ഇവിടേക്ക് പോവും. ഒന്നും ചെയ്യല്ലേ ഇവിടെ. കിഷനാണെങ്കിൽ പനിയുണ്ട്. ഇപ്പോഴും കിഷന്റെ അടുത്ത് കോണ്ടാക്ട് ഉണ്ടാവും. എപ്പോഴും ഇല്ല, പക്ഷെ കളിക്കും.
ഇപ്പൊ അവന് എന്നെ കുറച്ച് പേടിയൊക്കെ ഉണ്ട്. അച്ഛനമ്മ അതല്ല ഇപ്പൊ കൊറേ ദിവസം അവൻ കൈപ്പറമ്പിലൊക്കെ ഉണ്ട്. കൈപ്പറമ്പ് അത് അവന്റെ അമ്മേന്റെ വീട് സ്ഥലമാണ്. അവിടേക്ക് സ്ഥിരം പോകും. ഓ ഈ സംഭവം കൈപ്പറമ്പ് എനിക്ക് ഭയങ്കര സമാധാനം. ലുലുവില് പോയിട്ട് നമുക്ക് രണ്ടുപേർക്ക് ഈച്ചൊരു കാർഡ്. എനിക്ക് 114 പോയിന്റ്സ് ഉള്ളൂ. എനിക്ക് ഇപ്പൊ ഉണ്ടാക്കിയ 1800 പോയിന്റ്സ് ഉണ്ട് കളിച്ചിട്ട്. ഞാൻ ഉണ്ടാക്കിയതാ. അതല്ല, നിങ്ങക്ക് അത് വെച്ചിട്ട് പെയിന്റ് വാങ്ങിക്കുന്നില്ലേ? പെയിന്റാ പൂച്ചേച്ചല്ലോ വെച്ച്. ഞാൻ ആ ഡാൻസിങ് റോബോട്ട് ഞാൻ നിനക്ക് തരാൻ വേണ്ടി നിൽക്കുന്നു. പക്ഷെ അമ്മ വേണ്ട. ഡാൻസിങ് റോബോട്ടും പിന്നെ മറ്റേ ബൈക്കും എടുത്ത് ആ 200 വേണം. അത് ആ ബൈക്ക് നിനക്ക് കാണിച്ചു തരാൻ വിചാരിച്ചു. പറ്റിയില്ല. അപ്പൊ ഈ ബിറ്റോൾസ് അല്ലേ? അല്ല, ബൈക്ക് മറ്റേ റേസർ പോലെയാണ്. റിമോട്ട് കൺട്രോളാ എന്നല്ല, ഇറേസർ റബ്ബർ പോലത്തെ ഒരു കാര്യം. അതിനകത്ത് നമ്മളിങ്ങനെ ബൈക്ക് ഇങ്ങനെ ഓട്ടിയ ബാക്കിൽ നിന്ന് ബബിൾസ് വരും. മമ്മിക്ക് തോന്നാണ്. പക്ഷെ ബേബി ടോയ്സ് ആണ്. ബേബി ടോയ്സ് ഒക്കെ വയ്ക്കുന്നത് അവർക്ക് നമുക്ക് 1500 കിട്ടി. അവർക്ക് നിറ്റൻഡോ സിറ്റി PS5
energy. And we have also given the TPU rate max at the reference temperature of 25 degrees Celsius. In this polynomial equation, we have to first give the initial value of theta, then we have to input the first order coefficient and second order coefficient. T leaf we have already given. Same in the condition of phi, we are giving the initial value of phi and then first order and second order coefficient. So once we have given these are not we are giving the parameter constant values of all of this using the T leaf value and the Vmax, Jmax, TPU rate, RD values. This temperature response function is estimated. For each of the parameters estimated, you can go back. I mean, I have already provided in this slide, as you can also go back to the video and the PPT that where I have explained the temperature response functions in detail. Next, the code will take you to the FECB equations. In the FECB equation, the output that we are getting is net assimilation rate. That is, using these temperature response functions, the FECB equation. Now we have calculated Vc max at a particular temperature. What is the carbon dioxide condensation point at that temperature? Kc and K naught at that temperature. We have calculated again we have given an input for the electrons per oxygenation, electrons per carboxylation, J value. In order to estimate J value, we have given the incident PPFT. So the incident PPFT into 1 minus the leaf reflectance into 5PS2. 5PS2 has also been estimated using T leaf for that particular temperature, and beta PS2 is nothing but a constant value. So using all these input that we have given, these are the temperature response output. I is an input, beta PSI is an input, lambda R is an input. Using that, Q2 is calculated. Q2 is used in this equation. Again, Jmax is calculated from the temperature response function. Theta is also calculated from the temperature response function. So using the outputs from temperature response function and the inputs that we have provided initially, J is calculated and J is used over here. Now in case of TPU also, we have calculated the TPU at a particular temperature, and that is used for calculating the TPU limited photosynthesis. So the output of the FECB equations is the minimum of all these three values minus RD, and RD also we have calculated using the temperature response functions. If you see here, there's a term CI which we haven't used as an input. So what the code does is the code assumes an initial value of 0 for CI. So first they will calculate the net assimilation rate with CI equal to 0. So once we have obtained the net assimilation rate, the code takes you to the Ball-Bury equation. Now in the Ball-Bury equation, again we know the output is the relative humidity at the surface of the leaf, carbon dioxide concentration at the surface of the leaf, and leaf stomatal conductance. So these are the outputs for Ball-Bury equation. So we have provided the intercept and the slope value. From the FECB module, we are getting AN. By giving the input of relative humidity, the HS is calculated. Then by giving the input of atmospheric carbon dioxide, CS is calculated, and one boundary layer conductance also we are providing. From that we can get the total conductance. We can get the estimation for the GSW. The code does that, and then the output of this is leaf stomatal conductance, that is GSW. So once the ANet from this is used, AN, B0, B1, atmospheric carbon dioxide is used for estimating CS, RH is used to find out the relative humidity at the surface. All these outputs are obtained. Now once these outputs are obtained, the code will take us to the stomatal water stress. So in stomatal water stress, we know this function is used, that is we are using a stomatal water stress of 0.3, and that 0.3 value will be will be multiplied with GSW. That is the stomatal water stress is actually affecting the stomatal conductance. So whatever is the stomatal water stress that we are obtaining from the stomatal water stress linear model, we will multiply it with the GSW, so that GSW is also incorporating the stomatal conductance affected by the water stress it experiences due to soil moisture conditions. So from the set of constant values, temperature response functions are calculated. Using those outputs of temperature response function, the FECB equations outputs are generated, and net assimilation is obtained with the CI value of 0 initially. Then that net assimilation along with the constant parameters that we gave in the initial step, leaf stomatal conductance is estimated. Leaf stomatal conductance is adjusted for stomatal water stress that we are giving here as an input. Now next what will happen is, after all this AN, now we have got AN and GSW. Now CI will be calculated using this formula. So initially we gave a CI value of 0. Now using this CA value that we are giving as an input, net assimilation that we have got, the GBW which we have provided as an input, and the GS that is obtained from Ball-Bury equation and corrected for stomatal water stress, and the diffusion coefficients for boundary layer and the stomatal water stress, which is 1.37 and 1.6. CI is calculated. Now if you see this equation, this is nothing but that simple equation where we estimate AN as a function of CA minus CI into the stomatal conductance to carbon dioxide. If you see module 3, I have done the explanation of how this how AN is obtained as a function of the difference in the concentration gradient of atmospheric carbon dioxide and intercellular carbon dioxide, as well as the stomatal conductance to carbon dioxide. So that equation is rearranged to obtain the CI value. Now if you remember, we had started with the CI value of 0. So after getting this AN and GSW and using the input values of boundary layer conductance, we calculate CI. Then the code will look if the old CI is equal to this estimated CI. So old CI is 0, estimated CI, if it is not equal to 0, what it will do is it will again replace that new CI with the old CI. So CI equal to 0 will be replaced with the new CI estimated, and then all of these equations will be again, this is an iteration, so all of these outputs will be generated again and CI will be calculated again. It will check if the what we took here, which is the presently the new estimated value of CI is again equal to the CI that is estimated to the next step, and if it is equal, it will go in another loop. If it is not equal, it will continue the iteration. So this thing will continue as long as the CI that is considered here is equal to the CI that is estimated using the formula. Now once this loop is completed, and say we are getting a CI value in the before time step equal to the CI value in the next time step, it will finalize these outputs. That is, it will finalize that we have correctly got the net assimilation rate, we have correctly got the intercellular carbon dioxide concentration, and we have correctly got the conductance. Now after stomatal conductance to water, after that what it will do is it will calculate the T leaf using this equation. So there is an equation in here where T leaf is calculated using this formula. So here T means it is T leaf, so using 0.047 0.0130 previous T leaf, as T leaf is estimated using this formula, and then after that if it will check for the old T leaf. So if the old T leaf is equal to the new T leaf that is estimated, then the final solution of ANCI, GS and T will be same. Otherwise it will replace this new T leaf that is estimated in the temperature response functions, and then from the beginning it will for that new T leaf it will estimate this VC max. I mean all the temperature response functions, which will again continue in this loop. It will go here, it will check CI is equal to or not. If it is not, it will continue this thing, and then if it is the previous time step and the next time step CI value is coinciding, then it will use these value, it will finalize this result and calculate T leaf, and if the new T leaf that is calculated is the same as the one in the previous time step, then it will finalize that these are the stable outputs that we are getting. So this is how the coupling process of photosynthesis and stomatal conductance happen. So I'll show how we can do it in the code. So here as an initial this one we will new file. I want to see in which directory I am working, so I'll do get working directory, and yes, I am in the required directory that I am working in. So then I'll load the library biocro. Now I want to work with a module that has got, now till now we worked with FECB module that estimates photosynthesis, and Ballberry module that estimates leaf stomatal conductance. Now there is a module in biocro that combines these two modules together so that we get the processes, the process where photosynthesis is impacting stomatal conductance and stomatal conductance is impacting photosynthesis. So that module we will check through get all modules, and we see here that we are talking about C3 photosynthesis. So there is a module called C3 assimilation. Now I want to know what are the inputs in that module, so I'll do module info and paste the module name within this. and then I will run this line and I'll get what are the inputs and what are the outputs. So unlike the 2 or 3 earlier modules that we had looked into, this has all the combined input parameters of both FECB and Bolbury equation. So atmospheric pressure is there. We have B0 and B1, which is the parameters related to Bolbury equation. Beta PS2 is a parameter related to the RUBP regeneration for limited photosynthetic rate. Atmospheric carbon dioxide, electrons per carboxylation in oxygen is used in the RUBP regeneration limited photosynthetic rate. GBW is used to calculate CI. GS minimum is nothing but there is always a minimum value of stomatal conductance that will persist. Stomatal conductance is never going to be 0. So we have to give a very small value which is basically numeric to not bring any numerical instability. G star C is a scaling parameter for carbon dioxide condensation point. EA activation energy. Jmax is the Jmax value at 25 degrees Celsius. C and EA are the scaling parameters and activation energy for Jmax. KC, C and E, scaling parameter and activation energy for KC. Same for K0. Atmospheric oxygen 5 PS2 PS2012. This is the initial the first value, first order, the baseline 5 value, the first order coefficient and the second order coefficient. Q absolute is the incident ppfd. RD again dark respiration rate at 25 degrees Celsius. CNA EA scaling and activation energy. Relative humidity, what is the stomata water stress that is experienced. Temperature of the air, theta 012 again baseline theta value, first order and second order coefficient of the temperature response polynomial function. Leaf temperature, and this is for TPU rate, that is at this value TPU rate max is the value at 25 degrees Celsius. Entropy term, deactivation energy, activation energy, scaling parameter. For VC max we have Vmax 1 as the 25 degree Celsius maximum electron transport, maximum Rubisco carboxylation rate at 25 degrees Celsius, and scaling and activation energy. And if you see here, all the outputs combined, that is from FECB we get assimilation rate, from Bolbury we get these three parameters, that is stomatal leaf conductance, carbon dioxide at the surface, concentration at the surface, and relative humidity at the surface. CI value is also an output in the C3 assimilation, gross assimilation, stomatal conductance to carbon dioxide, photorespiration, and I did explain how there are a lot of iterations happening. So all these outputs will be obtained. So in order to run this module using evaluate function, we have to first create an input list to run for C3 assimilation, and then we see that there is a lot of input over here. If you see here, there's like a number of inputs, so individually inserting this value we can do that, but what I'm going to do over here is there is this biocro module is parameterized, that is we have all these values, the input values for various crops like willow, soybean, miscanthus. So out of this, soybean is only the C3 photosynthetic plant, so I'll use the soybeans parameters to run this biocro C3 assimilation. Now if you see, so if I could, let me show you what are the parameters in soybean. So soybean $parameters, you can see there are a lot of parameters over here. So if you see, okay, let me put it as a one not. So if you see here, there are so many parameters in soybean for a particular type of soil. The soil field capacity, sand content, soil saturated, all of these are soil related parameter. This is related to leaf area index, nitrogen related, Vmax. This is the Vmax one that we require. Then there are so many other parameters that you might not be aware of. Then there is atmospheric pressure we require as an input. We require all these values. So from here we see G star, J max, EA, KCC, KCK naught, phi, all these values that we require for running the C3 assimilation module. See, all of these we require to run C3 assimilation module. This also we require. This also we require. This also we require. Carbon dioxide, atmospheric carbon dioxide, O2, B0, B1, GS minimum, beta PS2. I think that's about it. So all of these parameters we require for running the C3 assimilation module. So since it is quite difficult to input each of these values into each of the parameter name, what I will do is there is a command called within. So if you type in within over here, you can see that in this within, if you put in some data, you can see an example over here. So within a particular data, if you open the curly brackets that input some of the values, all of the data which is coming within air quality will be used along with these parameters. So in my case, I don't have any extra parameters to input, so I will use input. I'll define a parameter input C3 assimilation and say within soybean parameters curly bracket, all these are the parameters that I require. These are the parameters that I require, inputs that I require. So I'll just paste this within this curly bracket. So the entire parameter values that has been used in the soybean biocro I'll be using these parameter values. Now when I run this, I'll get an error saying that GBW is not found. So in that case, what we will have to do is we will have to input GB value. So GBW value is not an input for the soybean module, soybean biocro. So what I'll do is I'll remove GBW from here, or put the GBW value is equal to say 2.9. Again, when I run it, they're saying Q absolute value is not there. So I'll go to Q absolute value and give a particular value of Q absolute. Usually 1500 is the value that is used. So where is Q absolute? Okay, so I'll put in the value of 1500. Then again, when I run this line, they are saying RH is not found. So I'll put a value of RH of 70% relative humidity. Again, let me run and see. Stomata water stress is not found. So stomata water stress, we had seen in the stomata water stress linear module that a stomatal water stress of 0 means the plant is extremely water stress. 1 means there is no water stress. So right now I am just taking the value of no water stress, which stomatal water stress is equal to 1. Hopefully we can see that okay, temperature value is also not given. So let's give a temperature value of 30 degree, and then when we run this command again, tea leaf is not given, so let's give a tea leaf of 28 degrees Celsius. Then finally, so now all of the values, that is all these atmospheric pressure, B0, B1, beta, PS2, all of these where we have not given the values explicitly are using the values that were used for soybean biocro. remaining all this GBW, Q absolute, stomatal stomatal water stress, relative humidity, temperature and tea leaf we provided separately as input. Now again, in order to run this module, I'll use the evaluate module command. What is the name of the module that I'm using? The input quantities required is input C3 assimilation. So when I run this, I get the outputs. I'm getting assimilation rate is 27 micromoles of carbon dioxide per meter square per second. Conductance is this much. Intercellular carbon dioxide concentration, surface carbon dioxide concentration, total assimilation rate, leaf stomatal conductance. See, 6 iterations. So that means that the 6 iterations were required to make the results stable. Then RHS is the relative humidity at the surface of the leaf. RP is the rate of photorespiration. So this is how we coupling of photosynthesis and stomatal conductance is done.